Okay, let's start. Good morning. So today, I'd like to finish this discussion about functions. I had written this down now for the third time, and hopefully this will be the last time. And we're going to be on our way afterwards. This week, the main item is to introduce the real line more rigorously, but not completely rigorously, and specifically talk about these two things called supremum and infimum throughout this class. And if you keep taking more and more analysis classes, supremum and infimum are two items that you keep using over and over again. I also wanted to, I'm going to take attendance today. So the way that's going to work is that I have an attendance sheet, and I want you to write your last name and then first name and then sign it, okay? So let's start here. Okay, any questions about anything? How is the problem set? Have you guys started working on it? Any questions about it? Yes?
I'm a little bit struggling with like 1 to C, trying to prove that that's a function.
Okay.
I mean, I know that I can't do it by contrapositive. That requires me to think of too many things at once.
Yes.
I think I'll go check the book on that.
Well, I mean, I would suggest, so we're going to cover what it means for a relation to be a function today, and hopefully with that it's going to be easy. So you want to be able to use something like this vertical line test, but of course in that problem things are more abstract. So I really want you to, even in this abstract setting, I'm calling it the vertical line test because that's the power of abstraction. In a sense, you can take something intuitive and try applying it into a more abstract setting. Yeah. Any other questions? Okay, so let's remind ourselves the situation. We have two sets, x and y, and I have a relation which was, by definition, an element of the power set. In other words, R is a subset of the Cartesian product. R is said to be the graph of a function if the following statement is true. For any pairs of points, x1, x2, x1, y1, and x2, y2, in the relation, if the x values are the same, I want the y values to be necessarily the same as well. Okay, so this is basically something like the vertical line test. If you were to start with the graph of a function and think of it as a shape, in other words, think of it as a relation, well, you would realize that this vertical line test is logically pretty much this. It's nothing else. Okay. In this case, that means that for any x value, there's a unique y value that is related to it using R. Let me write it here. Given any, I should be careful here, not any arbitrary x value, but really any point in the domain of R. So R should relate that x to some point in y to begin with. Otherwise, there's nothing to do. So given any x in the domain of R, there is a unique y in y such that x comma y is in R. Now we abbreviate or we denote this y as f of x. We denote this y by f of x, okay, which is now the formalism that you're familiar with. So when you read something like y equals f of x, it's really sort of like an abbreviation of all this stuff. So that's sort of like a high level way of saying all these things. this is sort of like a lower level way of implementing that idea. Further, putting A equals domain of R, we write F. So this is the more common notation that we're going to use. F colon A arrow Y for this situation, and call F the function defined by R. Maybe I should be more careful here. Let me say call F from A to Y the function defined by R. Yeah, there's an attendance sheet going on. Please make sure you're signing it. Now, whenever you see something like this, maybe I should ask you, at this stage, is there anything you should be worried about in whatever I'm saying, apart from understanding of it, of course? Now, you should be careful about definite and indefinite articles when you're using English to describe mathematical stuff. Now, I didn't say, for instance, here, call F a function defined by R. I called it the function. And here, too, I called it the graph. This really implicitly says that there's a unique such thing. And I'm going to leave that as an exercise. There is no two functions that is defined by the same relation. If a relation defines a function, it defines a unique function. So, if a relation R defines a function, that function is unique. Okay, that's a nice exercise. And finally, to relate this notation to the relation notation, we put R equals graph of F. Finally, we put R equals graph of F, which is this. X comma f of x, these are the set of pairs, such that x comes from A. Any questions about this so far? And so let's finalize this third method of defining new sets out of old sets. Well, given any two sets x and y, I'm going to denote f of x comma y, capital F of x comma y, to be the set of functions from x to y. And really, analysis is all about function spaces or function sets. Well, let me write it here. Denote by capital F of capital X comma capital Y. I like to use semicolon, but it doesn't matter. To be the set of all functions from X to Y. So it has to be defined everywhere. Set of all functions. Okay, I would like to give an example about all this stuff, but let me just say that for our purposes, for the purposes of calculus, it turns out that this set of functions for arbitrary sets is too general, right? Typically, for our situation, capital X is going to be an interval. Capital Y is typically going to be an interval, or it's going to be the whole real line. So this is going to be a set of real valued single variable functions. And furthermore, instead of looking at any function whatsoever, because functions can be very bizarre and very pathological, let's say, we're going to rather look at functions that have certain properties, like continuous functions, or differentiable functions, or integrable functions, and so on. And so those are going to be specific subsets of this set of functions. I would like to give an example about all this stuff, but before that, are there any questions? Okay, has anyone signed the attendance sheet? Okay. Seventeen. Bad at counting. Good. Okay. Let me add as a remark as well. Every operation that we define for relations apply for functions as well. So you can talk about the domain of a function, image of a function. You can compose functions. You can try inverting functions and so on. So all relation operations apply to functions. And this is where things are getting complicated, okay? Because of the following. I said something like, oh, you can take a relation and you can invert it, which is just flipping the x and y coordinates. I'm saying you can do the same thing for functions, but now the problem is that inverse may not be a function anymore, because we're talking about relational inverse, not functional inverse. So we're going to have to spend some time on things like conditions that allow you to say that, oh, if a function has this and that property, then its inverse is also a function. So here's an example. Let's see. Let me denote by capital X the interval from, let's say, -1 to 2, endpoints included. Let me denote by capital Y the whole real line. And I want to have a function from x to y. Oh, let's also take a subset of this so that we can think about the restriction operation. So A, let's say 0 to 1 closed. So this is a subset of x. And I'm going to define f from x to y. So -1 to 2 to r. And so this is a syntax that you're going to see very often. You can write f of x equals this, which gives you the formula of the output. Or you can be sort of like more functional, and you can write it like this. You start with a typical sort of, the name of a typical element here. And then instead of using this arrow, you use what is called the barred arrow. So this is giving you the formula. And let's start with something rather straightforward, x squared. Okay? So this syntax really is telling you that f of x equals x squared. Now, let me also point out the following. When I'm talking about functions, I really would like to use this notation. So when I'm saying I have a function f, I really want to just use the letter f. I don't want to write f of x. Because there's a small distinction. F is a function, but technically f of x is the value of the function f at the value x, at the input x. Okay? So there's a distinction there. So f is the function. So f of x is the value of the function f at the input value x. At the So in a sense, when I'm thinking of the function, I'm thinking of a graph. When I'm thinking of f of x, I'm really thinking of as a point, thinking of it as a point, but possibly variable as I vary x. Okay? Now in this case, of course, I can just draw the graph of it. And so let's start like this. So I'm going to start with something like this, and I'm going to delete pieces. So this is 1, and let's say somewhere here is, okay, let me try to be a little bit better. So like this, then this. Okay, this was the sketch. Now, in this formalism, you see the input set is part of the function, in a sense. That is to say, just x squared defined on the reals is not quite the same function as this function. Its input is restricted. So this is not quite the graph of it. Its graph is the following. Like this, and then here it ends as well. Okay? So that's the graph of it. So this is -1. This is 0. This is 1. This is 2. And again, we can write here f or graph of f. What's going to be the case is that we're going to keep using the function f and the associated relation, that is to say its shape, as interchangeable objects. Now, so far we've been sort of like strict about logic, but as the course progresses, we're going to be more and more loose about things. So this, I can just say, let me just be specific here, try to be more proper. This shape is the graph of f. Okay. What is f of -3? Well, undefined. That doesn't make sense. Okay. So let's think about these things. What is the domain of f? So the domain should be those points in x that f relates to something. But in order for f to be a function, it has to relate any input to some output, okay? Which means that the domain of this is -1 to 2. So let me write it. How about the image? What is the image of f? So the image of a function or a relation, more generally, is the set of all those outputs, so vertical things, so the heights I'm looking at. Well, visually speaking, you could say it like this. I can determine if, let's say, this point right here is in the image by drawing a horizontal line and seeing if it hits the graph. Right? So for instance, what is f of 1? Of course, f of 1 is 1. So this height is 1. What is f of 2? Well, f of 2 equals 2 squared, which is 4. Well, that means that if I were to use a height, use a vertical line, use a horizontal line at height 5, let's say, I wouldn't be able to hit the graph of f, which means that 5 is not in the image. But certainly, any number between 0 and 4, 0 and 4 included, are in the image. And so the image of f is the closed interval from 0 to 4. Okay? Any questions about this? Now, in this case, for instance, if I were to use a horizontal line at height 1/2, well, it hits the graph of f at 2 distinct points, you see. But for the purposes of determining the image of a function, that is not an issue. That's going to be an issue when it comes to talking about this other property, which is called one-to-oneness. And indeed, this function is not one-to-one, which I hope we're going to talk about later. Possibly it's going to be in the problem set 2. Okay, so these are the two things. What else did we do with relations? Inverse. Okay, so for instance, this function, let's first start with the following. I can think of the function as a relation. It's just a shape, okay? And I can just invert it. Now that inverse, we're going to see in a second, is not going to be a function itself. But it's still a valid shape. In other words, it's still a valid relation. And because the inverse of f is not quite a function, I don't want to write f to the -1. That's sort of like a specific notation reserved for sort of functions that have actually functional inverses. But what I can do is I can put graph of f to emphasize that I'm really looking at this shape, and I can invert that. So that's a relation, this shape, subset of what, x times y, okay, to the -1. This was the notation for the inverse relation. So the inverse. Relation of the relation graph of f. Now all I need to do is to write down the definition. If you look at your notes or if you look at the video, well, the definition of this is the following. It's a set of all those y comma x's such that, well, x comma y is in the graph. Okay, now what does it mean for x comma y to be in the graph? Well, that just means that y equals x squared. So I can just write it like this. But of course, one should be specific about the input values as well, because the x values are restricted. Well, the x values can be only between -1 and 2. Okay. And again, perhaps even consolidating further, I can write it like this. X squared comma x. I just substituted here, this, such that this happens. Okay. Now, visually speaking then, how can I think of graph of f to the -1? Well, it's literally the following shape. I can take this shape, look at the main diagonal, and reflect it. That's going to give me yet another shape. So to sketch, so here is the main diagonal. It passes through 1, 1, of course. Okay, so this is 1, 1. I'm going to restrict it later, but right now I'm just sketching. Well, for the inverse, all I need to do is to flip x and y coordinates. That means I need to take this shape, reflect it along y equals x, geometrically speaking. Now, if I were to reflect 1, 1, well, it's going to stay the same, which means that this point is stationary, this point is too stationary. So imagine this, sort of flipping it this way. So now I'm going to have something like this. Any questions about this? If I were to take this parabola, reflect it along y equals x, I'm going to get this other parabola. So instead of writing y equals x squared, I'm writing x equals y squared. Okay? Okay? But one has to be careful about the restrictions. Now, this ends, so the left side goes all the way up to -1, which means that this is cut off somewhere here, let's say. So it is cut off exactly here. But it goes to the right to some extent. So really my shape was like this. So that means that when I flip it, this point is going to be 1, -1, for instance. So I need to chop it off here. And then this point is going to be somewhere here. So this shape you see now is this inverse relation. And you see the endpoints are sort of the reflections along y equals x. Okay. Any questions about this? And this is the mystery, okay? We talked about all this stuff, all the sort of abstract things and stuff, and then ultimately somehow if you draw things and if you follow the rules, things work out, and it turns out that the way things work out are sort of synchronized with the way you would understand things intuitively, in a sense. Now, for now, it's going to be the case, and as time goes by, things are going to get more and more complicated, and you're going to have to you're going to need to fine-tune your intuition so that it works better for more complicated things. But this is always an important thing to do. It's like we're going to have abstract stuff, try to make it concrete, try to draw it. Like, how do I draw this bizarre thing? Well, try to draw a caricature, and then try to make the caricature more and more accurate, okay? Any questions about this? Now, is this relation the inverse relation of graph of f of x, inverse relation of graph of f, is it a function, or is it the graph of a function? Any guesses? No. It's not. Why? How would you say this?
It doesn't pass the vertical line test.
Right, exactly. Right. So So I can use this line somewhere here. It hits the graph at exactly one point, but if I were to use, for instance, the vertical line in this coordinate system, the vertical line at x equals 1, it hits the graph at exactly 2 points. So this is not a function, but the inverse exists as a relation. So this is the relational inverse, if you want to emphasize. This is the relational. Of f. It is not the graph of a function. Any questions about this so far? Okay. Now let's look at the restriction of f to a. So we continue. So everything is the same. Now I want to look at, well, let me perhaps leave that as well. So this, what was the notation for the restriction? You write the thing, and then you put a bar, and then you put sort of like a subscript as the set. It's sort of like an evaluation or integration type of thing. So now this, so let's say restriction of f to a. Now this is a function. Using functional notation, I would write it like this. It's from 0, 1 to r. 0, 1. What is the rule? It's the same rule, you see. The rule is the same, but the input value is different, or the bounds of the inputs they're different, which means that that's a different function. Okay, it's a different function, but it's the same rule. Well, if I wanted to draw this, well, all I need to do is to restrict my domain even further. So I can write domain of f restricted to a. And this would be equal to 0, 1. Its graph would be this smaller piece. It's a subset of the original subset. That was the graph. So okay. So they are related somehow. Certainly one of them is the restriction of the other one, but they're not quite the same thing. Okay, what is the image of this? Well, you see now the image is different. It goes from 0 to 1. Because if I were to use, for instance, height 2, let's say, certainly the horizontal line at height 2 hits the graph of f, but it doesn't hit the graph of its restriction to a. Okay, you should think of it like that. So the image of the restriction is also the same interval. And now in this case, there is something terse going on because the domain of the restriction and the image of the restriction are both the same thing, but when it comes to the graph of it, clearly they're not the same stuff, right? Like the domain, I would think of it as this horizontal piece, and the image I would think of as the vertical piece, but this is sort of like the discrepancy between visualizing things and the in this formalism that we discussed. Okay. Now again, I can look at the inverse of f restricted to a. And in this case, the inverse itself too is the graph of a function, right? Because if I were to flip this along y equals x, it's going to pass the vertical line test, which means that f restricted to a is a function whose inverse is a function also. I'm not going to write it. I'm just going to leave it to you as an exercise. So the graph of the restriction inverse, which is another relation, is the graph of some other function. Some other function. Which we might denote by f restricted to a to the minus 1. Now I can say function to the minus 1. Denoted by f restricted to a minus 1. Called the functional inverse. Of the restriction. Okay. And going forward, we're not going to spend too much time on relations, even though they're going to show up every once in a while. For instance, later this week, we're going to talk about something called an ordered relation, which is an important structure that we have on the real line that, for instance, complex numbers doesn't have. But still. So another operation that we talked about when it comes to relations was this idea of composing relations. Let's not get into that. We're going to spend more time on those kind of things. Maybe tomorrow we can talk about recurrence relations or difference equations and all those things, and perhaps dynamical systems too a little bit. But let's look at this other operation, which was the image. So the image of the subset A under F, the notation for this is just this, okay? If you want to be more pedantic, you would rather write graph of F of A, if you want to use the notation from last week, but this is sort of like a more common notation. Well, this is just, let me just reiterate, the values of all those y's in R, such that for some A in A, f of A equals y, A being 0, 1, of course, over there. Well, this is nothing but this. So this is nothing but 0, 1. So the image of f itself was 0 to 4, but the image of A, the subset under f, is this other subset, okay? And I'm going to leave it as an exercise. So this is an exercise over here. That's an exercise. Let's say identify this. So exercise. F inverse, let's say, 2 to 5. What is this as a set? It's a nice exercise to think about. Now, what you should immediately say to yourself is that, oh, in this notation, I should think of f to the minus 1 not as a function, okay, but as a relation. And that is why, ultimately, I spend so much time on relations. Whenever you see a notation like this, f to the minus 1 of some set, that f to the minus 1 is not a function, quite possibly, but it's a relation. So this may not, maybe I should say it like this, may fail to be a function. And sometimes people call this the preimage of the interval 2 to 5 under f also. Instead of image, you call it preimage because you're bringing things back. You go the wrong way, in a sense. Preimage of 2 to 5 under f. That's the name. Okay. Nice. Any questions about any of this? Now let's talk about yet another way of proving things. It's another method that I would like to introduce. It's called proof by induction. Now this method is less restricted. It works specifically well for certain types of statements, but it is very convenient for those types of statements. Let's start with this. Here's another example of a claim and a proof. I'm going to use a direct proof again. So, for any positive integer, let's say, n, the sum of all those integers from 1 to that integer has a closed formula. So for any positive integer, right, so this was my notation, so this means integer. I'm saying look at all those integers that are, strictly greater than 0, positive ones. So in the textbook, this would be n with a blackboard bold. But like I said, I'm not going to use that notation. Then let's say the following. Then 1 plus 2 plus ... plus n equals, does anybody know the formula for this? There's a famous formula. Yeah.
N times n plus 1 over 2?
Yeah. That's the claim. Let's do a direct proof of this. Just to have another example. This is not yet induction, okay? This is not the new method. Well, let me do this. Let me define the left-hand side to be, let's say, S of n, sum of n in a sense. Put okay, then you see now I'm going to do some bizarre things. You're going to be like, okay, so I understand that this is a valid proof, but how did you come up with these steps? And this is where sort of really math sort of starts building on top of logic. Then 2 times S of n is the following. Let me just write it. So this is the first S of n plus 1 plus 2 plus dot 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 plus n. But then, of course, I can drop the parentheses here and then rearrange everything, because this is just the finitely many, it's a sum of finitely many terms. So perhaps a nice way of writing this is this. You write this underneath this in such a way that if this is increasing, you want to write terms in a decreasing order. So you want to write it like this. And then plus n minus 1 plus dot 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 plus 1 is the same thing. But then you want to consolidate using the same sort of columns if you want. And so you see, these 2 terms add up to n plus 1, and these 2 terms too add up to n plus 1, and likewise this too adds up to n plus 1. So I have a bunch of n plus 1s. How many do I have? Well, there are n many, which means that this has to be equal to n times n plus 1. Well, if twice S of n equals that, S of n has to be this divided by 2. Any questions about this? Okay, we have a couple minutes. Let me just say a few words without writing things down. It turns out that whenever you have a claim of infinitely many, let's say, statements, so you can think of this one claim as, oh, for n equals 1, this is true. For n equals 2, this is true. For n equals 3, this is true, and so on. So you have really, you can think of this as infinitely many statements sort of compressed. Whenever you have a family of statements indexed by integers, let's say, this method of induction becomes very powerful. And induction is all about, instead of sort of going directly like this, you relate the statement that is indexed by some number n to the statement that is indexed by the next integer, n plus 1. Okay, I'm out of time, so I'm not going to write anything down. Tomorrow we're going to discuss more what this induction is all about. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today I'd like to discuss this other method of proving things that are good specifically for certain types of claims, which is this proof by induction. And I want to start talking about numbers a little bit more because this week is really about establishing certain properties, let's say, of the real numbers. I should mention, well, some of you already started sending me emails and asking questions and stuff about the problem sets and setting up appointments. I would suggest, if you have any issues, just be proactive and set up appointments. And it's okay to have one-on-one meetings, or if you feel more comfortable, if you would feel more comfortable, I'm also okay with setting up one meeting with you and a couple of your colleagues and stuff like that. And our grader is also working at the math center, and he just told me his times. So I'm going to send an email later today probably. And so that's going to be another thing for you to make use of. Okay, are there any questions about anything we did so far? So induction is essentially based on the following idea. You look at the world and you observe a certain thing, certain phenomenon, and then you say, okay, this is what happens. So something happens this day, tomorrow, and so on. And as long as you could remember, that's how things worked. And then based on that, you deduce that tomorrow too, the same thing is going to happen. Of course, in reality, this is not quite correct. And there's a lot of philosophers and stuff back in the day that had issues with this reasoning. So for instance, you could say, oh, you know, every day, as long as I've lived, the sun sort of rose. That means that tomorrow too, I will see the sun at some point, and so on. That is not quite logically accurate, but still, in mathematics, it turns out that there's a correct way of doing this. And this is how it works. Let's say that you have infinitely many statements that are indexed by integers or some subset of integers. Say, how to write this? For each n, let's write it like this, starting at 1, where you start doesn't really matter, but what matters is that it's one-sided. It doesn't go to negative infinity, for instance. P sub n is a statement. Then the principle of mathematical induction, or mathematical principle of induction, states the following. In order to show that for each n, P sub n is correct, what you can do is the following. You can sort of chop it up into two pieces. If P sub 1 is true, so the first statement is true, and for each n, P sub n, so the truth of P sub n implies the truth of P sub n plus 1. So this is the first hypothesis, and this is the second hypothesis. Then, this was the if, then for each n, P sub n is true. That's the conclusion. Now, what is the idea behind this? You say, okay, P sub 1 is true. Somehow you verify this. And then let's say that the second part is also true. Well, if P sub 1 is true for n equals 1, this means that P sub 1 implies P sub 2. But because P sub 1 is true, that means that P sub 2 is true. And then plugging n equals 2 and so on. You keep going like this. The benefit of using this principle of mathematical induction is that, well, if you were to try to use this chain of reasoning, for a typical n, you would have at least n steps that you would have to go through, logically speaking. But somehow, principle of mathematical induction just compresses all that time you would need to verify each and every single step. And it says if P sub 1 is true, and then if you can go to the next step, then for all of them, it is true. Okay, this is somewhat abstract, and perhaps it doesn't even make sense too much in this generality. Let's look at an example. So I'm just going to look at that claim that we stopped last time. The sum of all integers from 1 to n. So for each n, so I'm going to start using this notation as well. So, okay. equals n plus 1 divided by 2. How many of you have seen this symbol before? This one? Okay, all of you. So this is basically a for loop, right? For loop in math. It just says add all k's for k from 1 to n. So sigma for summation. Okay? So now what is my p sub n here? My p sub n is this guy. Left-hand side equals right-hand side for n equals that n. So this is my p sub n. This is okay. Or maybe I should say some words here. So this part is called it's called the base step, or the anchor step, and this part is called induction step. If you want to have names for this. So this is called I start recording. Yeah. Base or anchor step. I had a chaotic morning, so with some plumbing issues at home, so I feel bad because I ended up leaving all that stuff to my wife to handle. So, and this is called the induction step. Okay, so I want to verify p sub 1 is true for my statement. What is p sub 1? You see, typically, when you're using induction, the first step is going to be something very obvious. But still, since this is the first example that we're doing, let's try that explicitly. Proof. So one thing you can say, you can start like we employ induction or something. We employ induction, base step, n equals 1. Left-hand side equals, what? It's just 1, right? Because I'm adding from k 1 to 1. What is the right-hand side? Well, 1 times 2 divided by 2, which is 1. So the left-hand side equals right-hand side for n equals 1. Okay, so the base step is true. P sub 1 is true. Now I'm assuming for the induction step that P sub n is true for some n. And then I want to show that P sub n plus 1 must also be true then. So let n be arbitrary. Suppose P sub n is true. We claim that P sub n plus 1 too is true. So you see, now I have something to play with. Somehow, what I want to do is, I want to take P sub n plus 1, so I have some expressions, and sort of rewrite it using P sub n. Okay? So let me start with this. K from 1 to n plus 1. Of course, I can split it so that I add up all the way up to n, and then I have an extra term. So this is the first part, and then plus n plus 1, the remainder. But I assumed that P sub n is true, which means that I'm allowing replacing this expression by the corresponding expression. So this is because we assumed P sub n is true. Okay, consolidating, what do I have? Okay, so what I can do is I can multiply and divide by 2 here, and n plus 1 plus 2, n plus 1 divided by 2, but then factoring out this n plus 1, I have n plus 1 times n plus 2 divided by 2. Maybe I should write it like this, n plus 1 divided by 2. And this expression being equal to this expression is exactly P sub n plus 1. That is to say, we were able to show that assuming P sub n, you can show that P sub n plus 1 too is true. Thus, by the principle of mathematical induction, we're done. By the PMI, principle of mathematical induction, the proof, let's say, is complete. Okay, that's a typical, and in fact, this is probably the best example of induction. Any questions about this?
Why are we just adding n plus 1 to the previous statement? Second step.
So here, for instance.
Why are you just adding n plus 1?
Well, I mean, because I had to say something. I wanted to verify that this sum, so the sum from 1 to n plus 1 equals this expression.
Right.
And I said to myself, well, how can I relate this expression to some expression that is included somewhere in P sub n? And then I said, oh, this guy really is this plus this, and I see this in P sub n. It's kind of awkward, I realize. It just takes some time to get used to these things. So because I'm assuming that P sub n is true, that means that I get to manipulate this expression. I mean, I can try manipulating this expression as well, but that's what I'm trying to do. And yesterday, we did, without doing this shenanigans, we just took this expression and manipulated it and got the formula again, right? So that was a direct proof. This is just a different proof. Now it turns out that given a certain statement, sometimes direct proofs are easier, sometimes induction is sort of pretty much the only thing you can do. Especially when it comes to like sums like this, induction is like very, very powerful, I think. Okay. Any other questions? So, well, logical perturbation here would perhaps suggests if you can come up with a similar formula for sums of squares. That is to say, if I were to put k to the 2 here, is there a formula for the sum of squares like this? It turns out that there is, but I'm going to leave it to you as an exercise. There's a trick. There are multiple tricks, but one trick that you can use is the following. Okay, what I'm going to do is I'm going to give you a third proof of this, which does generalize to higher orders, higher powers. Alternative proof. This is going to be a direct proof again, but instead of doing the manipulations that we did yesterday, I'm going to do a different manipulation, And this is based on the following idea. Okay. Now, from a sort of softer perspective, what you can say is the following. When I'm adding integers from 1 to n, the value of that sum grows quadratically. What do I mean by this? Well, on the right-hand side, I have an expression. It's a polynomial, in fact. And the largest term is n squared. Well, it turns out that when it comes to limits and stuff like that, the highest order term is a dominant sort of sum n there. Which kind of does make sense too, because, well, you can think of the left-hand side as some sort of like an integral, right? It's the integral of x, basically. Not quite. It's sort of like a Riemann sum. Like this. And then if you had this, let's say you do something like this. Right? That left-hand side is really this integral of this staggered function, which means that its integral is approximately the integral of y equals x. Well, the integral of y equals x is x squared divided by some number. Okay, so that grows quadratically. Especially as you're taking n to infinity, well, the two functions are going to, so the actual y equals x and the staggered function is going to get closer and closer in a sense. Their integrals are going to get closer and closer. And so in a similar idea, then you can say, oh, the sum of all squares from 1 to n is basically the integral of x squared, which means that it's up to a constant x cubed. So ultimately, when you're trying to come up with a similar formula, you should expect a cubic polynomial here. Any questions about this? You see, none of this is rigorous, but certainly the stuff that you learn in calculus and the heuristics that you can come up with should apply. I'm not saying it is rigorous, but at the very least you know something about what to prove. Okay. So the point is, underneath all this idea, is some justification for the following proof. So I'm going to do the following. I'm going to look at k plus 1 squared, which is k squared plus 2k plus 1. Okay, just open it up, or binomial formula, whatever. Solving for k, I have this. So k plus 1 squared minus k squared. Let me actually leave the 2 here. Minus k squared minus 1. Okay. Then substituting, right? Instead of this, I can just add up these terms. Oh, that's a terrible thing to do, perhaps. Certainly, it is more complicated to write down. But the beauty here is that now I have something telescoping, so that things are going to cancel. That's what I was aiming for. So opening up this sum, I have k from 1 to n, sum of k plus 1 squared, minus k from 1 to n, sum of k squared, minus, well, let's write it like this. Okay. Now this last term equals n, of course. I'm adding 1 n times. I don't know these, but at the very least, this is, 2 squared and so on, all the way up to n plus 1 squared, minus 1 squared, minus blah, 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 all the way up to n squared. This means that this sum, so this sum minus this sum is, well, n plus 1 squared minus 1 minus n. Okay, opening this up, n squared plus 2n plus 1 minus n, which is n squared plus n, or n times n plus 1. But I had multiplied it by 2, which means that's another proof. Okay, of the same statement. So you see, we saw 3 different proofs of the same statement. It turns out that this argumentation generalizes rather easily to higher orders. So if I wanted to compute the sum of squares, well, instead of the second power, I look at the third power, solve for k squared there's a k squared term, and so on. Okay, so I'm trying to get this telescoping sum business. Okay, so that things cancel out. Okay, so I'm going to leave that to you as an exercise to generalize to higher powers. So, exercise. Generalize to higher powers. So, let's say you define S of n comma p to be the sum of all p powers from 1 to n. And you want a closed formula for S of n comma p. So S of 0 is just n because number to the 0 is 1. And we just proved that S of n comma 1 is n plus 1 divided by 2, and so on. Okay. Any questions about these things? This is a rabbit hole, okay? A lot of people have been interested in being able to add up these powers. Again, from just this heuristic, you should expect already that this is a polynomial of degree p plus 1. Okay, you should expect that already as a heuristic. Here's another exercise. This is slightly more annoying. Prove by induction the statement that we looked at on Friday last week. Okay. No, there are certain. So the issue here is that if you were to take this as p sub n, it's not going to be as straightforward to write down the sort of like the next step. So that's sort of like the one sort of weak point of induction. Sometimes you have a statement, but then you don't know what p sub n works the best. Okay. So translating the statement that is given to you to sort of like a sequence of statements that is easy to prove and stagger like this. So you want to have some sequence of statements p sub n such that p sub n implies p sub n plus 1 in a rather straightforward fashion. You can always put things in a certain way, but then being able to prove things is a different matter, of course. So, okay. Any questions about anything. In the textbook too, there are more examples of proof by induction. I would suggest that you have a look at them and see. Okay, so let's go back to numbers. Now, in the textbook, Taylor goes through a lot of work, does a lot of work to sort of like at least justify how to construct one number system from another one. So there's a hierarchy. I'm not going to spend time on that because I think it is too abstract in a sense, and I'd rather spend more time on calculus stuff. But let me also give as a reference, in case you're interested, there's a textbook, which is like the classical book for these kind of matters. Anderton, Elements of Set Theory. If you're into sort of like these foundational stuff, and if you want to learn, if you want to have a look at how to actually build things, even numbers, for instance, from nothing basically, you just take the empty set and you start taking the power set of things, and then you take the unions and so on. So it's almost like assembly code if you want. It's like, it almost doesn't make sense, but ultimately things are sort of like formalized that way. So I would suggest having a look at that. This book, Anderton, Elements of Set for more foundational matters. So for instance, in this book, defining a set takes a chapter, defining a relation takes a chapter. There's like a whole chapter on construction, on constructing the real numbers and so on. It's not really the main focus of this class. And while it is good to know that ultimately you can construct everything from nothing for the purposes of calculus, I think it's a benign thing to just assume that things, numbers, work the way they do and be on our way. So let me mention a couple of things about these number systems. So we have, let's say, hierarchy of number systems. So when it comes to a number system, it's not just a set, like we discussed last week, but there are certain operations. You've already been using these operations, of course, but from an abstract point of view, it's good to sort of single out, oh, this is the operation, that is the operation, and so on. Now, you start with naturals. Then you go over to integers. Then rationals. Then reals. One thing that's going to be important for us is what is called the extended reals. So we had talked about these last week as sets, but I want to talk about the arithmetic operations. So naturals is this set, positive integers, but together with a couple of things on them, right? You have addition. You don't have subtraction necessarily. By that I mean, if you're not careful, by taking the difference of the wrong numbers, 5 minus 7, for instance, you would leave the system. So you have addition, but not necessarily subtraction. And then you have multiplication as well. You don't have division necessarily because the ratio of two integers, again, is not necessarily an integer. One other thing, of course, is what is called the order structure. Given two numbers, two integers, positive integers, you know which one is larger than the other one. Formally speaking, addition here is a function. From the Cartesian product to the set itself, and likewise for multiplication. And then this guy, you can think of it as a relation. Okay. So addition, this is a function, this is a function, this is a relation, and this is how we sort of define a certain structure. And of course, this is not a random relation. It has to satisfy certain axioms so that it works like less than or equal to sign that you're used to, and likewise for addition. Okay, I don't want to get into the axiomatics of this, but it is there. Some people are interested in these kind of things. Now, when you go over from naturals to integers, now you have addition, you have subtraction too. You see now you can subtract any two numbers. You have multiplication, you don't have division, and you still have the ordering. Okay. Now, if you want to be formal about things, you also want to be formal about what it means to go from here to here. In other words, you want to be able to construct integers from naturals. And so that boils down to this idea of handling integers or doing things with integers without saying that you're doing things with integers. In other words, somehow using these set theoretical operations that we discussed last week and what you already have, you want to emulate integers. Okay? Let me just mention this. Maybe I should ask, do you have any guesses as to how to emulate integers using naturals? And by emulate integers, of course, I mean I want to be able to do something like subtraction, but only using positive numbers. Yeah?
Could you somehow define all odd numbers as negative or just consider them negative? Have two sets?
You could, but then you still want odd numbers to be odd numbers inside integers. You don't want to break what you already have. Yes. That could be done. I feel like this is not something that you can just guess if you haven't seen it before. So you want to make sense of something like this using only integers, positive integers. So what you say, this really is the pair of positive numbers 5, 7. Okay? So this is a certain element in the square of the positive integers. Positive integers times positive integers. But then there's an issue because you know that this should be minus 2, which means that if you were to put 6, 8, that should be the same thing. Okay? So you're sort of like representing, you're emulating the negative integer minus 2 in multiple ways. Now it turns out that using this relation formalism, you can handle this. I haven't discussed this, but just like there's a multiplication for sets, there's also a division for sets or factoring for sets. And that is related to what is called an equivalence relation. I was thinking of discussing it initially. That's why there are all these like phrases for week 1 on the syllabus, but I decided not to spend that much time on it because things get abstract, this emulation business. But it turns out that there's a sort of like well-established way of doing this. Let me just leave it like this. Okay. And if this is sort of like confusing, you don't need to worry about it because for the rest of the class, and certainly for doing calculus, none of this really matters. Okay. I just wanted to let you know that there's a formal way of taking this and constructing this guy. How about rationals? Again, what you do is you look at ratios and stuff like that. There are certain tricks you can do, but let's write it. So now, if you have rationals, you have addition, subtraction, multiplication, but also division. Okay, and also the ordering, of course. Now, you cannot divide any rational number by any other rational number. The exception is 0, but it turns out that that's like a structural thing that you cannot really avoid. Because 0 really comes from addition, okay? And then when you have two operations, addition and multiplication, you have to say something like something has to happen, something has to give. Now, all the stuff, so going from here to there, is algebraic ultimately. Going from here to there, rationals to reals, now there's something non-algebraic going on. I have again addition, subtraction, multiplication, division, and order. I have one more property, it turns out, but we're going to get to that. And finally, we have extended reals. I think I'm going to say a couple words about how to go from here to there, because in the book too, they sort of like discuss this a little bit. I don't want to spend too much time. Again, it's not going to matter for calculus how exactly to go from here to there. But then from here to here, what you do is you also adjoin minus infinity and positive infinity, and pretend that they are also kind of like numbers. So I'm going to write it like this. Minus infinity, positive plus infinity, but I'm going to use closed brackets. You have, again, addition, subtraction, multiplication, division, and ordering. Okay. Now, all of these things have certain axioms and stuff like that, but I don't think it is really helpful to go through every single axiom. You can read about them on your own from the textbook or on Wikipedia or whatever. What you should know is that the technical term for this guy is that R, the set of reals, is what is called a complete, totally ordered field. So R is a complete, totally ordered field. Okay. The word field is about these four operations. Okay. Totally ordered is about this guy. Completeness is what distinguishes this rationals from reals. Maybe I should write that down. Let's try it like this. So this word, the word field, is about the algebra operations. This is about this. Completeness, I would like to spend some time on. Because completeness is, intuitively speaking, about not having any gaps. Okay, has no gaps. is a heuristic. So for instance, rationals 2 is a totally ordered field, but it is not complete. Maybe I should write that down too. Is a totally ordered field that is not complete. Okay. So again, this means that rationals have certain gaps. The point is that root 2 should be a number, but it's not there. It's not in rationals. Okay. This was an exercise that I had given you last week, and I think now is the time to discuss it. Okay. Claim. Okay. So, do any of you have any guesses, any ideas as to how to prove this?
Well, we can define a Q to be A, B, like A over B, where A and B are both integers.
Mm-hmm.
And we can also, I don't remember all, like, because I learned this in a different class, but I don't remember all of it, but I know we can do it with, what is it called? Not contrapositive, but
Contradiction.
contradiction.
Yes. Right, so you want to go for contradiction. You want to say it is irrational. Why would you do this? Well, I mean, yeah, I understand. It's pretty much the same word as far as I'm concerned. Yeah. So, but why? It's like, why can I not go for a direct proof? Well, if you think about it, so far we haven't developed any direct access to a number being not rational. That is to say, we don't have any conditions, as we know, that we know of, that tells you, oh, this number is an irrational number. The only thing we know is to distinguish if a number is inside the rationals. And so that's why it is natural to go for contradiction. Of course, there are sort of conditions that are direct positive, that give you positive access to a number being irrational. For instance, using continued fractions, some Diophantine approximation, blah, blah, blah. There's a bunch of methods, but they're slightly more advanced. So this is sort of a more accessible, let's say, proof. Say otherwise. So there are two numbers, positive integers, p and q. Here, q not 0, such that this is the case. Now I'm trying to get some contradiction. Squaring, I get 2 equals p squared divided by q squared. So that p squared equals 2 times q squared. This tells you that p squared is an even number. I'm going to leave it to you as an exercise that this implies that p is an even number. So here, this is a subclaim if you want. Okay, so it's a lemma if you want. Yes?
Would it be necessary to say that P and Q have no common factors?
Well, ultimately, I'm going to use something like that, right? Yes, but eventually true. So that's your exercise. Because the next step is going to be this, or maybe I should have done it before. Let me include it here, and that's going to be yet another exercise. So at this step, there's an exercise which is the statement that we can assume that at most one of P or Q is even. It's a weaker statement than what you're saying. But in the textbook too, they're sort of like a statement. They have a statement that is pretty much what you're saying actually. So, exercise. Can assume that at most one of P, Q is even. Next exercise is that Q is also even. Because if P is even, P squared is divisible by 4, blah, blah, blah. So, exercise. Q is even. But because of this exercise, these two exercises give you a contradiction. Okay? Any questions about this? Modulo the exercises, of course. Exercises, I think it's good for you to think about. And in the textbook too, there's a theorem really that is a more general statement than this, or more strong statement than this. And there's an exercise related to that as well, but this is what I wanted. The point is that this root 2 should be a number based on, the right-angled triangle, blah, blah, blah. You can just draw it. And if anything, it should be this number based on every other operation, arithmetic operation that I can do. But it's not a rational number. Okay? So what you do is you do some emulation, let's say. Using rational numbers, you emulate something like this. We're done. I think we don't have much time today, so I'm not going to continue. But tomorrow, I think I'm going to say a couple words about how exactly that emulation works. And so in the textbook, there's something called Dedekind cuts. It turns out that that is only one method of emulating. There are multiple methods. But I think that's a good place to stop. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today, the main item that I want to discuss is what I'm going to call 4 provable axioms about numbers. Provable because if you're careful about how you're defining things, you can actually prove things. These 4 properties, but we're just going to take them as axioms. Before that, I wanted to say a couple words about this thing that I mentioned yesterday, the set division. This thing that I said that one can use to sort of emulate one thing using some other thing, because one of your colleagues asked about it. And then I thought we might as well just at least discuss a definition so that you have everything you would need in principle to construct things. So you start like this. Oh, maybe before going into it, I should ask, how many of you are familiar with what is called modular arithmetic? Okay, some of you. Yeah, okay. So this is basically a generalization of modular arithmetic. Okay, so modular arithmetic is the arithmetic of your sort of like analog clock, let's say. So you would say that, okay, so if it's 9 a.m. now, and let's say I have 3 tasks ahead of me, each of them is going to take 4 hours. At the end of that, what am I going to see on the clock? Again, it's going to be 9 hours, right? So you sort of like add them up and then you subtract 12, blah, blah, blah. And so this is the abstraction that really governs how all this stuff works. So I start with a set and a relation R on X. So this just means that R is a subset of X times X. And I'm going to call R an equivalence relation if it satisfies the following 3 properties. And what I'm thinking of, really, is equality. Now, whatever this is, equality should be an equivalence, but possibly not vice versa. Okay? So I'm thinking about what are the properties of something being equal to some other thing. Well, first of all, anything must be the same, must be equal to itself. And this is the same thing. This is also true for equivalences. So this is what is called the reflexivity property. For any point in x, x should be related to itself. Geometrically speaking, right, if I think of R as a subset of the box, of the square, this really is saying that the main diagonal should be inside my R. Second is what is called the symmetry property, or symmetric. This says that if x is related to y, then y should be related to x. Okay. So for instance, less than or equal to relation doesn't really satisfy this. It satisfies what is called the anti-symmetry property. Geometrically, what does this mean? Well, if I were to take a point x here, and then a y coordinate like this, so that I have here x comma y, well, what is y comma x? I need to reflect it. So here is x, and then here's y, so that this point is y comma x, and this point is x comma y. I'm not saying that x comma y has to be in R, but what I'm saying is that if x comma y is in R, then so is its reflection. It is symmetric. Third, and this one is hard to draw a little bit, but it is still very important. It's called the transitivity property. For any 3 points, x, y, z, in x, if x is related to y and y is related to z, I want x to be related to z also. It's almost like less than or equal to, if you want. Even though less than or equal to doesn't satisfy the second property. Comma z. Okay. Examples. Exercises. Well, let's say x is 0, 1. Let me also introduce one more notation. Instead of writing x comma x is in R, you would write something like this. X is similar to y relative to R. Okay. Well, let's say that, let's define a relation, x related to y, if and only if x is equal to y. This is a silly thing, okay? Equality relation is an equivalence relation, but not vice versa. But nevertheless, this satisfies the properties. Another exercise, now connecting this to modular arithmetic with, let's say, time or clocks. My x is z integers. And let me define the following equivalence relation. The exercise is to verify that it's an equivalence relation. I'm going to say two integers, m and n, are equivalent, or they are related, if their difference is a multiple of 12. So m minus n is in 12z. Recall that this was my notation for the set of all integers that are multiples of 12. Okay. So these are nice exercises. Now, where does division come into play? Once you have an equivalence relation, for R and equivalence relation on X, and for X in X, I'm going to denote the set of all those points that are related to X under R, X bracket sub R or something. So X bracket sub R, this is a set of all those points Y in X such that Y is related to X. This is the equivalence class of X. So this is a subset, you see, of X. In other words, it's an element of the power set. And then X divided by R, that's the division, is the set of all those equivalence classes. Okay, so this is how you divide things. And you would read it as X mod R. Okay, so X mod R. Modulo R. That's the name. Geometrically speaking, thinking of these squares and stuff, what you're saying is the following, really. You have the first component X, okay, and then the second component X. And then my R is a certain relation, which means that it's a shape here. What you do is this. You take an X and you look at the slice of your shape that is vertical. You're looking at the vertical slice. This is that vertical slice. So let me say, is the vertical slice of R. Pretty much like iterated integrals and stuff. And indeed, ultimately, if you keep sort of souping this up with more calculus, iterated integrals really are about these divided sets and stuff also, it turns out. Okay? So in this case, X mod, the equivalence relation, is X itself, really, because if you were to think about this, the shape of this is just a diagonal, and the vertical slice has only one point. You get back X itself. In this case, you get modular arithmetic. You would write Z mod 12Z. So this is the clock arithmetic, if you want. Okay. You only count integers, though. You only count hours. You don't count minutes and stuff. If you wanted, you could amp this up to sort of like incorporate minutes and whatever, seconds and all that stuff too, but let's not get into that. Okay. This is like rather abstract. And this is basically the only other set theoretical construction you would need to take something and emulate some other thing. Okay. And if this is like too abstract, no worries. We're not going to need this really that much. It's very important, of course, but perhaps not for this class. Just to give you an idea, let's talk about how one can use this notion of an equivalence relation to emulate integers, so positive or negative numbers that are integers, using only positive integers. Yesterday we were talking about how one can go from one number system to the other one, and so this is sort of the formal way, or this is part of the formal toolbox that you would need to accomplish something like that. Again, I'm going to leave it to you as an exercise. So emulating all integers via only positive integers. It's not just integers, really, it's pairs of integers. So my x is going to be the Cartesian product of positive integers with itself. So the relation is going to be a subset of this times itself, so 4 times positive integers if you want. And so let me define the following. If I take a pair of integers, I want this to be the same as this other pair of integers if something happens. And of course, the trick here is that you know what you want to end up with. What I said yesterday was that I want this pair to represent what's going to end up as a minus b. So I want this to be really emulating a minus b. Using only positive numbers, I don't know what minus is. I only know what plus is. But somehow, I want this to really emulate this number. And so these two should be the same if this expression is the same as this expression. In other words, moving things around, so send this to the other side to get rid of the minus. A minus d equals b plus c. Okay? So this is what I want. Okay? And so what you can do is you can say this pair of integers is equivalent to this pair of integers if and only if this is true. So the exercise is to verify that this is an equivalence relation. And then one thing you need to do is to verify that somehow addition still makes sense with equivalence classes themselves and so on. Let me say one more thing. All this is abstract, but you can always try to visualize things. Because after all, what I'm doing is, well, I'm just, I have a mesh, right? I have a two-dimensional lattice, you would say. And I do certain things with, well, vectors, basically, integer-valued vectors. And so what I can do is this. So here is, let's draw it like this. This is the main diagonal. Here's 1, 2, 3, and so on. And then here's this, this, this. 1, 2, 3. Okay, so this is the first coordinate, x coordinate. This is the y coordinate. And I know the coordinates of these integer points. So for instance, this is 1, 1. And then this is 2, 1. This is 3, 1, and so on. Okay, maybe I should write it. Let me just write 2 of them. Now, 1, 1 really represents 1 minus 1 for me. That is to say 0. And likewise, 2, 2 should represent the same number, same integer. And so on. And really, when you think about it, in the set of integer-entried planar vectors, what I'm doing is I'm really thinking of all the pairs of numbers on this main diagonal as the number 0. So in a sense, this line, y equals x, becomes the integer 0. And this is why things get rather abstract here. So this line itself is 0 here. So using the notation, z now is x mod the equivalence relation. And likewise, for instance, 2, 1 should represent 2 minus 1, which is 1, which should be 1 ultimately. And so this number, this point, should be the same as 3, 2. Okay? So this line really is 1 in integers, and this line is minus 1 in integers and so on. Okay? And how do you add two integers? That is to say, two lines in the plane? Well, you just add using vector addition. I'm going to leave it to you. Okay? Okay. So you see, this is where things start getting bizarre. When someone asks you, it's like, what is really an integer? There are billions of different ways of answering it. Okay? And this is one way. So the right answer to the question, what is an integer, is really what you have already. Okay? Based on what you have, you can try emulating it multiple ways. This is not really the topic of this course, but it's good to know. Any questions about this?
It's really cool.
Yeah, it is, yeah. Now you can appreciate that in the beginning of 20th century, people were interested in the foundations of math. They were really concerned about whether or not things actually made sense. And also during the same time, people were interested in actually coming up with computers and stuff. And just like in assembly code, it really doesn't make sense. Ultimately, computers are all about zeros and ones, but when you're coding things, you're not using zeros and ones. But deep down, everything is zeros and ones. And in math too, everything ultimately is a set or something made up of sets. Okay? Now this is not the only foundation. There are alternative foundations. One foundation is what is called type theory, and the other one is called category theory. So even these are not unique implementations. There are multiple ways of doing the same thing. Okay? And if you take sort of like more advanced classes and foundations and stuff, I'm sure you're going to spend a lot of time on these kind of things later. But for the purposes of calculus, obviously these don't really matter, how integers are defined and so on. But still, just know for now that some people really make a living thinking about these kind of things. And it is possible, if you're good enough, to make a living thinking about these kind of things. Personally, these kind of stuff kind of make my brain hurt, so I do more calculus things. Okay, any other questions? Okay, we have this. Okay, so now doing similar stuff, you get to emulate this, that, blah, 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 and ultimately you get real numbers, okay? So now I want to say 4 things about real numbers. For us, they're going to be axioms, but really we can prove them, at least most of them. Four important, I'm going to say, provable axioms. Axioms about numbers. Axioms. Um, One is what is called the well-ordering principle. It says the following. If I have a non-empty subset of positive integers, then it has at least elements. So let's write it. Let S be a subset of positive integers. If it is non-empty, that is to say, if it's not the empty set, then it has at least elements. Okay. If you want to be formal about this, what is the least element? Well, you would try it perhaps like this. There is, let's say, an S star in S, some number, such that for any S in S, S star is, it bounds from below S. It's the same thing as saying that it has the least elements. Okay. Now, in fact, you can prove this using induction. And maybe on Friday we can sort of talk about it, because the proof is rather, it's slightly complicated. And the way I proved it when I was thinking about these kind of things, and I was preparing the class, it's sort of like a bunch of different proof methods sort of put together. And so it might be a nice exercise to have a look at the proof and sort of try to parse it, what type of logical stuff I'm using and so on. But for now, let's take it as an axiom. I'm certainly not going to deduct any points if you just use this as an axiom. And you should probably do that for this class. So here's a nice exercise. In this situation, really this S star is unique. Exercise. Has a unique least elements. In other words, I could have put an exclamation mark point here using the logical notation if I wanted. They're so unique. It's a nice logical sort of game. Okay, so that's the first property. Maybe on Friday we can think about how this is related to induction. It's not clear really, but it is true that this is equivalent to the principle of mathematical induction. You see, logic is bizarre like that. The second one is the so-called completeness axiom. Recall from yesterday that when I was talking about certain properties of the reals, I said, okay, so it is a complete, totally ordered field. And I said field is about, arithmetic. Ordered or totally ordered is about less than or equal to. And then completeness, I said I want to say a couple words about it. Now I'm saying a couple words about it. And this is really the most important thing, really, as far as I'm concerned. Completeness axiom. axiom. So this is a formalization of this idea that the real numbers has no gaps, okay? But this notion of having no gap really is not a rigorous term. So what you say is the following. You take a subset of real numbers, let S be a subset. If S is non-empty and it is bounded from above, if S is non-empty and is bounded from above, in a second, I want to talk about what this means really. Then it has a least upper bound. Well, maybe to emphasize, as a number in R. In terms of math, how could I represent that S is bounded from above? Any guesses? So I want to sort of clarify what this means, and I want to clarify this notion of having a least upper bound. So these two phrases are somewhat dubious. I want to make them more formal. How can I formalize this notion of a set being bounded from above? Any guesses? Yeah.
You could say for some element in R, every element in S is less than R.
Right? So, and if you're getting confused, think of the closed interval 0, 1. Okay, what is an upper bound? So something, you want to bound any number in 0, 1 from above by some other number, maybe 15. 1 is also sort of like a good bound, and in fact, that's going to be the least upper bound. So you want to say something like this. There's an M, real number, such that for any S in S, S is dominated, that's also something that you can say, by M. Okay? That's what it means for S to be bounded from above. I'm not saying anything about this M. I'm just saying that something exists. An upper bound exists. That's what I'm saying. Okay. How about S having a least upper bound? It's kind of one step further. So I'm sort of like looking at all upper bounds, and in a sense, I'm optimizing. I'm looking at the optimal upper bound. I'm being the most frugal. Maybe even sort of before trying to formalize it, let's try to look at an example. So here's an example. I'm just going to write down what I said about the interval and all that. And if you're sort of feeling uneasy about this, that's well warranted, because this class is really about understanding this axiom. Like it implies a certain things, and it takes a while to get used to it. Example. So let's say that my S is the interval, closed interval, from 0 to 1. M equals 2 is an upper bound. For S. Any number between 0 and 1 is bounded from above by 2. It's not the best upper bound, but it is an upper bound. Now what you can do is you can look at the set of all upper bounds of S. how can I represent this? Well, it's going to be a set of numbers, real numbers. Let's call it set of all those m's, such that for any s in s, well, for any s in 0, 1, m dominates s. Now, can I sort of write this in a much friendlier fashion? So this set includes 2. It includes 1 also. And when you think about it, it should include any number greater than or equal to 1. So this is just a bizarre way of writing the ray 1 to infinity. Okay? If this is not clear, it's a good exercise to really sort of go through the motions and try to formalize this idea. Now, this is really saying that this set of upper bounds has the least elements. Certainly, the least element is 1. Okay? Best upper bound, which is the most optimal upper bound for the set 0, 1, is 1. Okay? The point is, if I were to replace s with open interval 2, the answer would be the same. That's where things are getting somewhat bizarre. Okay? So any questions about this example before going into this formalization of the notion of a least upper bound? Okay, so let's attempt this. There are multiple ways of writing things more formal. Thinking of the least scary way of writing this. We might as well. Okay, so I'm just going to abstract out this example. And I would suggest that you do something like this as well. You look at the statement and it doesn't make sense. Just go to the example, the least complicated example you can think of that actually tells you something, that you can compute things. Okay? So, what do I need to do? First, I need to establish the set of all upper bounds for S, and then I want to say that it is a minimum. It is a smallest element. Well, not necessarily the set itself, but reals. So, then defining, let's say, U for upper bounds. For the set, there is oh, it is correct. Okay, so there is m star in U such that for any m in U, m star bounds from below m. So I look at the set of all upper bounds and I say there's a smallest one, there's a best one. Okay. Okay. Now let's look at this example just to compare it to this. What I said a minute ago is, or a couple minutes ago, is that the same idea should hold even if I were to use an open interval. Now I'm looking at S01 open, so endpoints not included. In American notation, this would be 0, 1. Okay, I'm using this notation. Now I look at U, the set of upper bounds for S. Certainly, 1 is an upper bound. and any number greater than it, 2 is an upper bound, which means that 1 to infinity is included. Now the question is, so far we have this. Does you have a number that is less than 1? In other words, is U, the set of upper bounds, equal to the set, or is it larger, possibly? Maybe let's draw a picture. Here's 0, here's 1. Okay? So this guy is S. This part is this. Now, I'm saying maybe U has more points. Well, how can it have more points? Which means that it's perhaps like a ray that starts here. Maybe it intersects S, is what I'm saying. Could that happen? And this, it cannot. And that is the third axiom. Okay? It is what is called Archimedean property. But let me just leave it like this. This really is equal. Oh, let me just say, in fact, by 3. Okay? And 3 is the Archimedean property. Okay. So, this was 2. Okay. 3 is the Archimedean property. Now, I'm saying that these are provable axioms because really there is no issue with taking these as axioms for this class, even though if you look at the textbook, because in the textbook they construct real numbers from rational numbers using these things called Dedekind cuts and stuff. They actually prove things. Because I'm not spending time on these construction business, I think it's better to just take these things as axioms. And then when you learn everything, and if you have some extra time and stuff, you can just go back and see how things are done in a more proper fashion. So 3, the Archimedean property. It says that if you have any number real, there's an integer that is greater than it. Okay. Not much to say, but one good way of using this, or one sort of version of this, is to sort of send this to the other side as a division, assuming x is not 0. You can also say this, maybe as an exercise. AP is equivalent to, for any x positive, there is an integer, positive, such that 1 over n is less than x. Okay. Well, maybe I should have said something about this completeness axiom. You can prove it using some sort of construction of the reals out of rationals. That's why we're not doing it. You can really prove Archimedean property out of the completeness axiom if you want it, but we're just taking it as an axiom. And the fourth one that is important is what is called density property of the rationals. which says that between any two numbers, oh, maybe let me put it this way, it's rather easier. For any x positive, there is, let's write it like this. There's a q rational positive such that this happens. Okay. Now, when you think about this, Archimedean property in this form is really a specific case of, or a stronger case of the density property for rationals, because 1 over n certainly is a rational number. And they're equivalent ultimately, I believe. And again, you can prove this using the completeness axiom. I'm just sort of exposing you to different sort of logical statements that are ultimately the same, because, you know, in a proof, this version might be more useful than this version and so on. Okay? So these are the properties that we're going to keep using over and over again throughout this class. Any questions? Okay. Now you see slowly things are opening up. Now another number system that I mentioned yesterday was this extended number system, or extended real numbers. In the textbook, they just say, oh, you have real numbers and then you adjoin to it these two symbols, positive infinity and negative infinity, and you use these symbols the way you would use in calculus. So you're not allowed to divide infinity by infinity and so on, but a number plus positive infinity is positive infinity and all that stuff. And positive infinity should be larger than any real number and so on. It is a bunch of properties. I'm not going to write those down. In the textbook, they mention a little bit. But I want to reiterate this idea of emulating. So that instead of saying, oh, I'm just adjoining these two symbols, positive and minus, you know, sideways 8, and I'm just treating them as special things, you can actually try to make sense of them using some sort of emulation. So let me just write it. Extended reals. The way I'd like to write it is minus infinity to positive infinity with close brackets, and this really stands for R union positive infinity as something, and then minus infinity. But instead of writing it like this, let me first draw the picture. The way I imagine it is like this. The real line is a line, 1, 2, and so on. And then somewhere here is yet another point that is denoted by infinity. And then somewhere here, there's another point denoted by minus infinity. Okay. Now the point is that how to make sense of this without saying I'm just adjoining this symbol and so on. Well, thinking of calculus, I can think of, well, lines passing through the origin in the plane. And then I can look at their slopes, okay? And this really does make sense. So one way to emulate extended reals is to say, I'm going to look at oriented lines in the plane. So via oriented lines passing through the origin in the plane. Okay. So the horizontal line, slope 0, is going to be my number 0. But I want it to be this way. Okay. Well, there is yet another line, y equals x, that has slope 1. That's going to be my number 1. And then this guy, slope -1 line, is going to be -1. But you see, the beauty of this is that as I increase the slope, ultimately I'm going to have a vertical line that is looking upwards. That's going to emulate for me plus infinity. The point here is that you can just avoid all this problems about defining infinity using this. Okay, it's the vertical line. You can I'm just giving you tools to be a politician when it comes to a mathematician, when it comes to being talking like a mathematician. And of course, if I were to have the line pointing downwards, that would be minus infinity. The problem now is that if I were to look at the line that goes this way, that gives me some other number. So what is its slope? It's again, so I guess I want to call this -1 because it is oriented, you see. Now you see I have two representatives of the number -1. I'm emulating, I'm over-emulating. But what I can do is I can quotient out. I can use this equivalence relation business to get rid of this. Okay. Maybe it might be good to say a couple more words about this on Friday, but this is all I wanted to say. Of course, for the purposes of this class, it really doesn't matter how you're thinking of this. You can think of the extended real line like this, or slopes of lines and so on. Okay, it doesn't matter. Thank you. This is it for today. I'll see you on Friday. Okay, let's start. Good morning. So I'm taking attendance today. There's an attendance sheet going on. Please make sure that you sign it. So problem set 1 is due tonight, and I'm almost done writing problem set 2. You're going to see it later today. It's going to be on Canvas. Now, I mentioned something about this. Recall that this well-ordering principle was one of the 4 fundamental statements about numbers, the first one. Maybe let's remind ourselves what it said. Does anybody remember what this well-ordering principle says? It's something very sort of silly in a sense, but somehow it's useful. Yeah.
There is a least element in a finite set.
In any set of integers, there's a least element. Okay, positive integers. And so maybe let's write it down. So without using these logic symbols, let's write it out explicitly, and I would suggest you do that too. When you see something, a statement that you don't see, you don't understand, it's a very good method to sort of rewrite it or paraphrase it using something else. If the statement is given to you in logic notation, turn it into plain English. If it is given to you as plain English, turn it into logic. Or maybe something is described as a geometric object, or maybe a shape was given to you. Then try to write it as a logical statement. Or maybe if something is given to you as a logical statement, well, try to draw it. Always try to transition between different ways of sort of describing things. Somehow, when you try to translate one mode to the other one, you end up sort of understanding it better. At least that has been my experience. So this well-ordering principle says any, of course, it has to be non-empty, right? Any non-empty subset of positive integers, let me just say ints, has a least element, has a min. And so we assume this, we took this as an axiom, but really we can prove it using the principle of mathematical induction. let's just do this proof because I think it is illuminating. Because the way I thought about the proof of this, and there are many other proofs of it, of course, sort of incorporates a couple of different methods. So I'm going to write it in a much more terse fashion, and then we're going to have a look and see, oh, here is sort of like an instance of direct proof or something like that. We're going to try to understand that together. So say S, a subset of positive integers, has no least element. Okay. Yeah, so here's what I'm going to do. By definition, S is a subset of all integers starting from 1. This set literally is the same set as this, of course. This is saying this is the set of all integers greater than 0, and this is a set of all integers greater than or equal to 1. These are literally the same thing, but you're going to see why I'm writing it like this in a second. Say n is such that S is included in the set of all integers bounded from below by n. But then n cannot be in S, because otherwise n would be the least element of S. N is not in S, for otherwise n would be the least element. Of S, because this assumption literally tells you that any element of S is at least n, right? Thus, n is included in the set of all those integers bounded from below by n plus 1, so that S really is in the intersection of all of these guys. But this set, the intersection of all these tail integers, if you want, is empty. Thus, S is the empty set, and that's the end of the proof. Oh, thank you. Did we all sign this attendance sheet? Okay, let me just count. So we have 16, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Good. Okay, so this is the proof, and really this is how you would see a proof out in the wild, so to speak. Okay, so let's try to understand this. What is going on here? So what would you say? What type of a proof is this? Is this a direct proof, proof by a contradiction, or proof by contrapositive?
Contradiction?
The other one.
Oh, contrapositive?
Yes.
Oh, okay.
So at least the way we stated was this, right? So if you try to turn this into a logical statement, this surely says that if S is not empty, then has a min. Now I assumed the conclusion. Say this doesn't hold. That is to say it doesn't have at least elements. So I'm really starting a proof by contrapositive. Obviously, it doesn't matter what these are called, but just since we're sort of thinking about these kind of things, I thought it would be good. So the general proof, the big proof, is a proof by contrapositive. So this maybe is a proof by contrapositive. That's the general scheme, the big proof perhaps. The big proof is this. So I'm assuming not Q, and I want to get not P. So what I'm trying to show is something of the form P implies Q, and this is the general method. I assumed not Q, and I'm trying to get not P. Okay? What else? Do you see any other methods here?
There's kind of like an induction.
Right? I didn't say it, but so I need a sequence of statements indexed by integers. So you see, this is my base step. And then I'm assuming this holds. And I showed that this is true. So let's try it. It also involves induction. The statement P sub n here really was that S is a subset of this guy. Are we all okay with this? So you see I'm saying, so P sub 1 is, it's obvious, okay, like I said, because we just assume it. And then what did we do here? We did base step, and then I assumed P sub n, and I showed that it is P sub n plus 1 is also true. Okay? So let's try that. P sub 1 is true if this is the case, okay? If P sub n, then P sub n plus 1. And really this subroutine, let's say, that was about induction, concluded with really this. This so that really implicitly says, oh, by the principle of mathematical induction, for each n, P sub n is true. Okay? For each n, P sub n is true. In terms of set theory, of course, this just means that S is in the intersection of all of these sets. Are there any questions as to how I switch from this to this? From the logical statement to the set theory statement? Yes?
I guess I'm not understanding why intersection is being used.
Because P sub 1 is true. That is to say, S is in Okay, let's write it. What does this mean? So, and P sub 2 is true, and, okay, and so on. Now, grammatically, this is sort of like a sentence with infinitely many ands. And you know, in standard English, this obviously doesn't make sense because there's no end to it. You would just say you're not making any sense. But Principle of Mathematical Induction literally says, in this context, when you're doing math, it's like you get to think of that infinite sentence as an actual logical statement. Okay, does this make sense? Just allows you to compress time like that, in a sense. And there's like even more advanced versions of induction that I don't quite understand. These are called transfinite induction, blah, blah, blah. But this is all we need. And, you know, when you're reading it like this, it's like, it's clear. Eventually, I hope it will be clear that, okay, so if S is in all of these, then it should be in the intersection. But underneath, that's really an instance of Principle of Mathematical Induction. Okay? So then how do I know that this is the empty set? Well, that's really an exercise. It's a nice exercise if it is not clear for you. I'm going to leave it as an exercise. That is to say, the intersection of all tails is the empty set. There's no number. There's nothing here in this intersection. But if S is a subset of the empty set, well, S has to be the empty set itself. Okay? Yes?
If you were going to do this as a proof by contradiction, what would you have started with?
What do you think?
I feel like it's kind of hard because you have like any non-empty subset of positive ins, and it's kind of hard to like negate both of those.
Okay. That's a nice idea, actually. Now, it turns out that really, this stuff that we're talking about when it comes to logic is really something mathematical. And this is called the Boolean algebra and stuff like that. And really, there's a certain arithmetic going on underneath. So let's try to understand this. Let's try to be more explicit. So, exactly. Yes. Yeah. Yeah. Should I write more? Like, I think you got it, but let's talk about it. So what I said was, okay, so if I wanted to do a proof by contradiction of this, recall that's what I said is sort of like the perhaps easier method sometimes because you assume more. Well, you say, okay, I want this to not work. Let's do some sort of logical arithmetic here. So, you're going to assume this, and you're going to come up with something obviously wrong. Now, it turns out that P implies Q is logically equivalent to not P or Q. So that means that these two cannot be at the same time false. So either P has to be false, so you don't have the hypothesis, or if you have the hypothesis, then this is false, which means that this has to be true. There's also sort of like an interpretation of all of these logical things as electronic circuits, which is lots of fun, and then you can do linear algebra with these if you want. But let's not get to that. And then what do? You distribute this negation, and then when you distribute, you have been looking into De Morgan, it says that the negation of or is and, right? So if you take the complement of union, it becomes the intersection of the complements. Okay, so this becomes not P, and not Q. But not P is just P. Okay, so you assume that you have a set S such that it is non-empty and not the conclusion, doesn't have a least element, which is what your colleague suggested. And then you sort of manipulate things to get another proof. Okay. Any questions? Yes.
I still have a question on that. S is subset of intersection of P over.
This?
Yeah. Yeah, I could understand this line. Yeah.
You're okay with this?
Yeah.
Are you okay with the idea that saying that for each n, P sub n is true is the same thing as S is a subset of this and it's a subset of this and okay.
But in my understanding, the intersection of they who over or equal to n, it should be like, for example, when n is equal to 1, it means like there's a site, it starts as 1, but for example, if the intersection of they over equal to 1 and they over equal to 2, there doesn't including 1, right?
Yes, exactly.
But F should be less or equal to, I mean, F should be a subset of the over equal to 1. Should we use union here? That's my question.
Maybe I could draw a picture. So here is the real line, and I have all the integers. Okay, goes on like this. Okay, this is 0. I assumed that my subset S is somewhere here, and then we showed here that, or we realized that this is the same thing as saying, oh, it's after this. S being here is saying that S is included here. Okay, but then it has to be included here as well. And then it has to be included there.
Oh, I got that.
This is a very bizarre way of writing empty set. Okay, running tails. Yeah. So later on, when we start talking about lim sup and lim inf, we're going to do something very similar to this. We're going to look at the tail, and the tail is going to sort of like keep running off to infinity. And we're going to take a limit like that. Okay? Any other questions? Okay, good. Now, what is the point here? The point is that if we wanted, we could have proved this well-ordering principle, which we did. But it's also okay to just assume it. Take something as an axiom, okay? And so when something is an axiom, that doesn't mean that you have to assume it. It means that for whatever reason, it just makes things easier to assume it. And indeed, for instance, there's a famous example of this coming from Euclidean geometry. Some of you are physics majors, so you're probably interested in these kind of things. But so Euclid was this guy who did all this, plane geometry stuff, triangles and all that stuff. One of the axioms, and this is sort of the template, let's say, of how we do math today, even though he didn't sort of make these things very explicit as far as I understand. He had a bunch of axioms, and he was trying to deduce everything about like triangles and stuff like that. The area of this is that, and the angles are like this, and all that stuff, from certain axioms that he had. And one of the axioms he had was that, okay, what was it? Yeah, so one of the axioms was this. If you have a line, and if you have a point outside the line, then there's a unique line passing through this point that doesn't intersect with this. Okay, this is the famous fifth axiom of Euclidean geometry. And for a long time, people were interested in whether or not this fifth axiom was redundant. Oh, they thought maybe you could prove it using the other axioms and stuff like that. And then it took a long time, because this is ancient Greek stuff. I guess back in the 19th century, people started realizing that really this axiom is independent from the other ones. And realizing this, people sort of started perturbing this axiom. Oh, what if you just don't assume this axiom? Given any line and a point outside it, there are multiple lines passing through this point that is not intersecting this. And then this led to what is called now hyperbolic geometry. People like, I think, Lobachevsky, of course, Poincaré, many other people, Minkowski, many other people did important things about this. And then ultimately, people realized that, oh, you know, even without assuming this axiom, you can do geometry. And then this led to, well, general relativity and special relativity, which then led to GPSs and all that stuff, which then led to you being able to track your DoorDash guy when you order something. So you never know. People were just looking into axioms just for the sake of it, because it was fun, and then 200 years later, it becomes something important. So in a sense, the things that are unjustified now that we do in pure math, you should think of them as, oh, these are potential sort of like revolutions, or, you know, conveniences, perhaps, 500 days later, okay? So someone has to put the work in today so that people can figure it out, people can learn how to use it later. Okay, any questions about this? Of course, this is like outside this class, but if you were to take a class on differential geometry, blah, 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 this is like a big area, okay? Very important. You can do physics too, of course, if you're interested in those kind of things. Okay, so now I want to introduce these famous or infamous objects or notions called supremum and infimum. And in problem set 2, you're going to have a bunch of problems about this. Probably you're going to see one problem about induction, possibly. And then the rest is going to be all about manipulating these supremum and infimum. And throughout this class, you're going to write sup and inf thousands of times, okay? And suffice it to say, it's going to take a while to get used to it, get used to these ideas. And this class is really all about understanding supremum and infimum. On Wednesday, I said it's about understanding the completeness axiom. They are really the same thing. Completeness axiom says that supremum and infimum make sense, in a sense. And so here's the definition. Let's first start with supremum. Infimum is sort of like dual, in a sense, just like minimum is dual to maximum. So let me give you the definition, and in a sense, in a second, I'm going to talk about this heuristic, or how I think about it, these things. Sup is going to be this. It's a function whose inputs are subsets of reals, and whose outputs is the set of extended reals. So I take an A, and I'm going to send it to some point here. There are three options. And this is going to be a piecewise defined function, okay? If A is empty, that is to say, if it's the empty set, I have to think about that. Sup, I'm going to define as minus infinity, okay? Oh, is empty. Okay. If A is non-empty and is bounded from above, then by the completeness axiom, there's a least upper bound. That is to say, there's a number. Okay? There's an optimum upper bound for A. Supremum of A is going to be that number. Least upper bound. To emphasize, this is a number, real number. Finite, not infinite, not this bizarre stuff. It's an actual number. And the third option is A is non-empty, but is not bounded from above. Yes, is not bounded from above. If A is non-empty and is not bounded from above, I'm going to define the sup as positive infinity. Okay, this is the definition. So sup of A is basically the least upper bound. I want to include plus or minus infinity as well. It's going to be convenient. Then on top of this, I'm going to define the max function, similar to this, except that the max function is not going to be a function defined on all subsets. So it's going to be a partially defined function. So let me write it like this. So this is my notation for a partially defined function. It's like doesn't take every single input. It's a relation if you want, but it's not a defined. It's not defined everywhere. And this is always going to have real outputs. And I'm going to send A to sup of A if sup of A is an element of A itself. Otherwise, undefined. Okay, so now this is the definition. Before going into inf and min and the adaptations of these to functions, I want to do two examples actually. But even before that, are there any issues or do you have any questions about at least the syntax, let's say? I know it is rather abstract, but we're going to deal with this. Okay. So let's start simple, okay? You always want to start simple. Again, I want to start with, let's say, the closed interval from 0 to 1. So A is this. Let's draw a picture, like so, 0, 1. And of course, this goes to positive infinity. Any guesses as to what the sup of A is? It should be an upper bound. 1, okay. So how do I think of this? The way I think about it is the following, okay? So this is the guy that I'm trying to sort of clamp down on. Think of it like that. Let's say you go out to the sort of to a shoe store and you're trying to get a new pair of shoes and you have your feet and stuff, but you don't know your size. But there's a machine there, okay? You put your feet in, then you sort of like clamp it down. It tells you what your size is. Think of it like that. So this is your foot, and the sup is sort of like the top part. There's a similar sort of mechanism if you're trying to sort of scan something on the printer, right? Like you have paper, you put it on the tray, but then there's like these clamps. You sort of like start wide, and then you sort of like make it tight so that the printer doesn't have any issues. Same idea. So you start somewhere here, okay, 15, whatever. It's an upper bound, but I want to optimize it. Least upper bound, you see? A is non-empty, and it is bounded from above. I know that the supremum is a number. So it's a number. It's a real number. What is the best one? Well, you go all the way here, but you cannot go any further. That's the point. Okay. So far, what we said is sup of A cannot be larger than 1. Okay. Why? Because, let me write it. So how can I argue that this is the case? Well, I can say it like this. If, let's say, sup of A is 1 plus epsilon, epsilon is going to be always a positive number. Okay, some number larger than 1. Well, what I can do is I can optimize this always, right? I can replace 1 plus epsilon by, I don't know, 1 plus epsilon divided by 2. That's obviously better bound than this. Is a more optimal, more frugal upper bound. But I need something more. I also want to say that sup of A cannot be smaller than 1. Okay? This is slightly more complicated to see. Any guesses as to how I can argue that this is the case?
You just say that for, you say 1 minus epsilon is a thing, then say that is less than 1? Because 1 is in the bound?
Sorry, say again?
So you say you say sup of A is 1 minus epsilon,
Okay.
and you have to prove that, well, the least upward bound means that everything is greater than or equal to it. And so 1 minus epsilon is necessarily less than 1.
Okay. But, okay, there's an issue there. Okay. Oh, I guess what you're saying is that, but 1 is in the set. I see. Okay. Okay, good. Let's write it. Because if it was like this, then 1, which is a number in A, is not, so it is a larger number than this. But this is supposed to be an upper bound. Is larger than sup, which is a contradiction. By definition, sup of A must dominate from above any number in A. Okay. Any questions about this? Yes?
What happens if it was an open interval instead of a closed interval?
Exactly. Your argument would not quite work. So you need to adjust that a little bit. That's why I was thinking of something else. So the next step is going to look at the open interval, but we're going to get to that. Before that, though, I want to mention something, and this is an important way of arguing about things. So this is a proof of something, okay? And this is going to happen often. You're going to prove something, but there's not going to be a claim. What is the claim here? Any guesses? Yes?
Supremum of A is 1.
Exactly, right? So the claim is this. And this is also an important method, okay? Sometimes when you're in the middle of something, so this is not going to be the main claim. This is going to be sort of like the sub claim in a larger proof. And so you're going to be confused perhaps, and you're not going to know what exactly you're trying to prove. But it is good to sort of like just start sort of thinking about what can be done, okay? And after you prove something, look at what you did and sort of extract from it the statement that you ended up proving, okay? That's the first sort of moral of this argument. Second moral is this. Now that we realize this is the claim, reverse engineering this argument leads to the following general principle. And this is what Terence Tao calls an epsilon of room, okay? And this is like something that you use all the time in analysis. Analysis is about negotiations, okay? It's all about barterings. So if you're trying to show this thing is equal to that, well, if you're doing algebra, well, you compute it, and it is that or not, okay? If you're doing analysis, you say, well, could they be approximately the same, okay? You bite the bullet, you say, okay, this is true up to an epsilon, and then maybe I can take epsilon to 0, okay? Up to an error, this equation is true, and then for whatever reason, perhaps, I can take the error to 0. Okay? So this is the principle of using an epsilon of room. This is very powerful and very useful, so I'm going to write it out. So, well, I guess maybe I should write down as well two ideas. To show A equals B, well, let's put it like this. A equals B is the same thing as A is less than or equal to B, and A is greater than or equal to B. That's the first thing. If you want, this is sort of like a logical factorization. Second is an epsilon of room. Epsilon of room. A is the same thing as B if and only if, well, their distance is bounded by epsilon for any epsilon. For any epsilon positive, A minus B in absolute value is bounded from above by epsilon. We didn't quite use this actually, just use this, but still. Now, I call this the distance between A and B, because all I do is I look at the difference and then I take the absolute value so that I have a positive number or non-negative number. because distances are supposed to be non-negative numbers. Next week, we're going to talk about something called the metric space. This is the third structure, or the further structure on the reals, or any number system that we're interested in. That's going to be very useful. Okay, we're going to look at metric, the distances, the notion of a distance in the abstract. Now, in the textbook, they don't discuss it in the chapters that we look at. They sort of talk about metric spaces in abstract when it comes to sort of the second class, the multivariable calculus part of the SQL class. But I thought it would be good because we are going to need to use sort of at least one other metric space, which is going to be a space of functions. Turns out that for us, it's going to be important to figure out what is the distance between two functions too. So I thought it would be good. So we're going to spend some time on that next week. So let's look at the second example. A is open interval, 0 to 1. Oh, before going into this, what is the maximum of this guy? Right, so I can say, oh, I first computed the supremum. I realized that the supremum is 1, but then 1 is in A. Then by definition, maximum of A is defined as the supremum. Okay. So now we look at the open interval. And in fact, let me do it like this, because we're just looking at the sup. So I want to figure out what is the sup and what is the max. Any guesses as to what is the sup of A is? Okay, that's an attempt, right? So let's try to see if this is true. Well, again, I'm going to try to use the first principle here, first idea. I need to show that sup of A is bounded from above by 1, and 1 is bounded from above by sup of A. First of all, sup of A exists because it is a bounded set. It's non-empty. Okay, maybe I should write it. By the completeness axiom, sup of A is a number that exists. Okay, there are also numbers that don't exist, I guess. But it's a number. It's a real number. Now you're going to realize that this first part follows through. Okay. If 1 plus epsilon is were an upper bound, well, 1 plus epsilon divided by 2, 2 is an upper bound for this. So this part goes through immediately. Okay. So it cannot be greater than 1. So how do I write it? It is bounded from above by 1, as before. The question is it actually equal to 1, or can it be any number less than 1? Any guesses as to how to argue? Let me just say that the claim is true. So I also want that sup of A is at least 1.
If sup of A equals 1 minus epsilon, then 1 minus epsilon over 2 is still in A.
Exactly.
Yeah.
You can do that. That's sort of like this is basically the same argument. You can argue like that. You can just say that's true by the Archimedean principle. Between any two numbers, there's a number. There's a bunch of different ways. Okay. So since your colleague mentioned this, I'm just going to leave it as an exercise. What is the maximum of A? It doesn't exist. Okay, that's the difference between this guy and that guy. Sup always works. Max doesn't always work. Why? Because sup of A is 1. 1 is not in A. In order for max of A to be defined, that max, that sup, has to be inside. So okay. We don't have any time to go into inf and how to do this with functions. We're going to start next week with a discussion about that. And I want to do a problem that is slightly more complicated, but I think this is a good place to stop. Thank you. Have a nice weekend. I'll see you on Monday.